Now we come to solve the acceleration part of the problem. Let's start by sketching the system again. I'm not trying to work out geometry this time, so I'm going to be a little bit rougher. Okay. AB normal plus AB tangential equals AA normal plus AA tangential plus AB relative to A normal plus AB relative to A tangential. We know that AA tangential is 0. We know let's come now and look at our picture and work out the directions of these vectors. AA normal is a vector. Remember that the normal acceleration is omega cross r, which I can rewrite as minus omega squared, scalar vector r. The normal acceleration always points back towards the center of the circle. So AA normal points from A to O. AB normal points from B to C. AB tangential is in the same direction as VB. We don't know whether it will be going up or going down until we know the sign of alpha BC. AB relative to A normal points from B to A. AB relative to A tangential is vertical. Okay, we can work out the magnitudes. AA normal is, I'm just going to work with magnitudes here because I'm doing the geometry. Omega is 4 squared, r is 0.1, so that's 1.6 meters per second squared. AB normal is 1.5 squared times 0.2, 2.25, 4.5 meters per second squared. AB relative to A normal equals 3.125 squared times 0.16, which equals 1.5625 meters per second squared. That doesn't make sense, but I see that my mistake was here. Sorry about that. Okay, now we can try and draw this giant expression in geometry form. Starting with the ones we know. AA normal, we know its direction, its magnitude, 1.6. That direction, this angle here is 90 minus theta. Then we add on to that AB relative to A normal, which is horizontal and about the same size, 1.56. And then AB relative to A tangential is going to be vertical, but we don't know which direction it's pointing. Now we come to the other side of the equation. AB normal is pointing down. This angle here is theta, so this angle here is theta. So it's at 90 degrees to this, and that's much smaller. I've drawn it quite big, but we see it's about a quarter of the length of the others. There's AB normal, and then AB relative to A normal is perpendicular to that, somewhere like that. Now we see that when we construct the acceleration diagram, I can't work out exactly which direction things are going without getting all the sizes exactly right. I've sketched them approximately. It looks like we have something like this, but to actually solve for this, I'll need to do it to scale. So I still like to sketch the acceleration geometry, but I like to solve the problem using the vector algebra because I make fewer mistakes like that. I'll do that now very quickly. I hope this has been helpful. The most important thing to do with these problems, to get good at them, is to practice, to try different problems, but not just to try and do them once fast and check for the solution, but to try and understand why things work. with all of these problems, you can see I've solved them two ways, using geometry and using vector algebra methods. Doing those both ways. Obviously, when you're writing a test and you're under time constraint, you won't do things two ways. But while you're learning how to do it, it can really increase your understanding of the problem. The other thing that I want to say is everything I have done, all of these problems I have solved in essentially vector methods. Even when I've done scalar calculations, I've done those scalar calculations to put them into a vector diagram. I'm adding vectors together, I'm not adding scalars together. So you must commit to understanding and working in the vector format. Thank you very much for your attention and good luck.